Hello again, everybody. Grab your s'mores stuff because today we are talking about Graham's Law. Not that kind of Graham. Anyway, Graham's Law deals with effusion. So effusion is the tendency for gases to escape through small holes, and it turns out that lighter gases move faster. And that kind of makes sense conceptually, right? Something that's small is going to be really quick, where something that's kind of big and lumbering is going to take a while to effuse. So Graham's law is a little bit different. It allows us to compare rates of different gases. And you should note that down here in the equation, A is on the top of the left-hand side, but it's on the bottom on the right-hand side. And conversely, B is on the bottom on the right-hand side, but it's on the top on the right-hand side. So they are going to flip spots top to bottom as we go left to right. So let's see how this looks in a problem. So we're asked to compare in number one the rates of effusion of hydrogen and oxygen at the same temperature and pressure. So we are going to try this two different ways. We're going to try one where we put hydrogen on top, one where we put oxygen on top, and we're going to compare and see if there's a difference. So let's put hydrogen on top to start. Our equation says that the rate of our first gas, in this case we're picking hydrogen, over the rate of our second gas, in this case we are talking about oxygen, is equal to the square root of their molar masses over one another. But remember, they flip. So oxygen is on the bottom on the left, it goes on top here, so it's 32.00. Remember, oxygen is diatomic, two oxygens, that's why it's 32, not 16, over the square root of hydrogen's molar mass is 1.01 times 2 is 2.02. So you do the math there, and you will get that the rate of hydrogen over the rate of oxygen is equal to 3.98. Another way to read that is to say that the rate of hydrogen, the rate of effusion of hydrogen, is 3.98 times the rate of effusion of oxygen. Okay, so that was putting hydrogen on top, and then on the right-hand side, oxygen was on the top numerically. So let's flip these. What happens if we accidentally did it the other way, right? What if we did rate of O2 over rate of H2? Well, we'd have rate O2 over rate H2. That is equal to a square root. And just for the sake of argument, let's do it this way. It turns out that a square root over another square root is the same thing as this, the square root of a big fraction. So this might be an easier way for us to attack this. The molar mass of H2 is now on top, that's that 2.02. O2 is on the bottom, 32.00. These both have units of grams per mole. I'm just not writing them to save a little bit of time because they're going to cancel out. And when you do that math, you will get 0.25. So if you read that, it would say the rate of oxygen, or the rate of effusion of oxygen, is 0.25 times the rate of effusion of H2. And so if you look at those two things, even though the numbers look like we've done something totally different, they say the same thing, right? In one case, we say that hydrogen is moving about 4 times faster. In the other case, we say that oxygen is moving about 1/4 of the speed, or 4 times slower. So they mean the same thing. You can do it either way. Either of those would be considered correct. I personally prefer to do what's in blue here, and the way you can predict how to do this is to put the lighter gas on top of the left-hand side, because that's going to put the lighter gas on the bottom of the right-hand side, and you're going to get a number, therefore, that's always greater than 1, because the numerator will be greater than the denominator. The other thing to just take note of here is that we predicted that lighter gases move faster, and that's what we've seen, right? Hydrogen is moving about 4 times faster than oxygen, and hydrogen is lighter. Okay, so let's try another one. Let's deal with hydrogen, and this time we're going to compare it to an unknown. So this one's going to be a little bit weird, right? Let's set up our equation. If you look at number 2, here's what we know. We know that the rate of hydrogen H2, over the rate of some unknown gas, we'll call that UK, we're not in Britain, but unknown in this case, is equal to the square root. Again, you can square root the whole fraction or have a square root over a square root, they do the same thing, is equal to the molar mass of UK over the molar mass of H2, because we have to flip the left-hand side when we go to the right. So what do we know in this? Well, if you look back to the problem, it says that the hydrogen effuses 9 times faster. So that looks a lot like what we said up here. So what that means is that this entire left-hand side is equal to 9. The rate of H2 is 9 times the rate of UK. That's the ratio. So that is equal to the square root of the molar mass of the unknown, which is what we want to find, over the molar mass of hydrogen, which we know is 2.02. So that looks kind of nasty to solve, but you have a square root. Let's get rid of that. Square both sides. 9 squared is 81, is equal to the molar mass of the unknown over 2.02. Multiply both sides by 2.02, and you will get that the molar mass of the unknown gas is equal to 164 grams per mole. Remember, grams per mole is a unit of molar mass. Technically, I should have had the molar mass right here, 2.02 grams per mole, so that's where that unit is coming from. It's not just coming out of nowhere. All right, let's try one more. This time we're going to compare neon. Neon is a noble gas on your periodic table to butane, which is a gas that has a formula C4H10. We don't really know the molar masses of these yet, so I'm just going to put neon on top just to get one up there. So we know that the rate of neon over the rate of this butane, which is C4H10, is equal to the square root of the molar mass of butane, which is C4H10, over the molar mass of neon, which again is straight off of your periodic table. So there are some things that we know. We are told that that neon gas travels at an average of 400 meters per second. 400 meters per second. Meters per second is a speed, also known as a rate. So this is our rate. So we can fill in here that the rate of neon is 400 meters per second over the rate of butane is what we're trying to find, so that's C4H10, is equal to the square root of their molar masses, but flipped. So the molar mass of butane goes on top. That happens to be 58.14 grams per mole when you do 4 carbons and 10 hydrogens. For neon, it has a molar mass of 20.18. So let's do some math here. Let's do the math in the square root, and at the same time, let's multiply this rate C4H10 to the right-hand side. Let's get it up into the numerator. So when we do that, we'll be left with 400 meters per second, that was the rate of neon, is equal to the math inside of the square root turns out to be 1.70 when you do the division and take the square root. And now that is times rate of butane, which is C4H10. Obviously now all we have to do is divide away 1.70, and so we're left that the rate of butane, C4H10, and this is ultimately what we wanted to find, is equal to 236, and the units that are uncancelled are meters per second. So you can see 3 different applications of Graham's law. We can use it to solve a myriad of different things, but it's kind of cool to be able to compare the speed of different gases. And we'll test this in lab by having a little race between 2 different gas molecules.